So today we're taking a deep dive into electron clouds, and we're going to figure out why there's so much more than just like empty space around an atom.
Yeah, and we'll look at why thinking of them more like a symphony where the music's kind of happening everywhere at once.
Ooh, I like that. A
Yeah.
symphony, not just little planets going around.
Exactly, yeah. It's really about probability, not fixed paths, you see.
Okay.
Those electrons, they're constantly in motion, and the cloud, what it represents is where we're most likely to find them, not where they are at any given time.
Okay, so we're talking about probability, but then here's my question. Why don't these negatively charged electrons just crash right into the positively charged nucleus? I mean, opposites attract, right?
Yeah. Right, and that's where we have to bring in quantum mechanics.
Oh, boy.
I know, but it's really cool stuff.
Right.
See, electrons, they behave like both particles, A and D waves, and this is what the de Broglie hypothesis describes.
So it's like both at the same time?
Yeah. Think of it like a wave in the ocean. It's spread out. It's not localized to one specific point, right?
Okay, so we're not talking about a tiny little billiard ball just, whizzing around.
Yep.
We've got this wave-like electron.
Yeah.
And how does that keep it from spiraling into the nucleus?
Well, so the wave-like nature of the electron, we describe it using something called a wave function, and this is a mathematical expression.
Okay.
And we can't directly see it, but it's a tool. It helps us to calculate that probability of finding that electron in a particular location.
So that's what determines where it's most likely to be.
Exactly. And so those probabilities, then when you visualize them, well, that's what forms the electron cloud.
Hold on. So this wave function, what you're saying is it tells us where the electron is most likely to be.
Mm-hmm.
But we don't know, exactly where it is at any given moment.
Yeah, exactly. It's a little bit like if you're trying to pinpoint the exact location of one bee in a beehive.
Okay.
It's got to be in there somewhere, and you can probably take a pretty good guess where it's most likely to be, but you can't say, this is it, this is the spot.
Gotcha. That makes sense.
Right.
So the electron cloud, it's really like a map of probabilities,
Yeah.
not some fixed path.
Precisely.
Okay, but these clouds, they're not just like random blobs, right?
Definitely not.
There's got to be some structure.
Oh, yeah.
Yeah.
Electron clouds, they take on very specific shapes, you see. And these shapes are, they're actually crucial in how atoms interact with each other.
Really?
Yeah, these shapes are, they're determined by what we call atomic orbitals. And each of these orbitals, they have their own unique energy level.
So each orbital is like a specific vibe that electron can have.
Yeah, that's a good way to think about it.
And each vibe's got its own distinct shape.
You got it.
Okay.
And just like, you can't have like half a vibe.
Right.
The energy levels of these orbitals, they're quantized.
Quantized
Meaning they can only take on specific discrete values. This is one of the key principles of quantum mechanics.
All right. So we've got these quantized energy levels.
Yes.
That then lead to these specific orbital shapes.
Mm-hmm.
So tell me more about these shapes. What are we looking at here?
Well, the simplest one, that would be the s orbital, and this one is spherical.
Like a ball.
Yeah, like a fuzzy ball.
Okay.
Centered around the nucleus.
Gotcha.
Then we have the peak orbitals.
Okay.
And these are they're dumbbell shaped, so you can picture them with two lobes extending along different axes.
Wait, so if I could actually see an atom with p orbitals, it would look like it's got these fuzzy dumbbells sticking out.
In a way, yeah.
Huh.
But remember, we're always talking about probabilities here, not not solid objects.
Right.
So these shapes, what they represent is the regions where that electron is most likely to be found.
Okay, so it's not like an actual physical dumbbell.
Exactly.
But these shapes, they have huge implications, right?
Oh, yeah, they do.
Yeah.
Huge.
Yeah.
Well, for example, the shapes of these orbitals, they directly influence the shape of molecules.
Oh, wow.
Think of a water molecule. It's shaped like a V, right?
Right.
Not a straight line.
Right.
And that's because of those dumbbell-shaped p orbitals involved in the bonding.
So the shape of a water molecule, something we just, take for granted every day, that is dictated by these invisible electron clouds.
Yeah, pretty cool, huh?
That's wild. What else should we know about these orbitals?
Well, there are also D and F orbitals, and these get even more complex in their shapes.
Oh, boy.
But the main point here is that each atom, it has a unique set of orbitals, kind of like a fingerprint,
So each element's got its own unique set of orbitals. with electrons just like buzzing around in these specific energy levels, these specific shapes.
Yeah.
So it really is like an electron party with the orbitals as the designated dance floors.
I like that. Yeah, that's a good way to picture it.
And just like a dance floor, there's only so many people that can fit on there.
Exactly.
Each orbital, it can only hold a limited number of electrons.
And that is because of the Pauli exclusion principle,
Okay.
which states that no two electrons in an atom can have the same set of quantum numbers.
All right. Quantum numbers exclusion principle. This is getting a little
technical.
Yeah, a little technical for me.
Yeah.
But if I'm getting this right, this principle, it's basically setting some like ground rules for this electron party, right? Making sure that every electron's got its own like unique dance move and space on the dance floor.
Exactly.
Okay.
And this principle, this is actually key to understanding how the periodic table is arranged.
Oh, wow, really?
Yeah. So the way those electrons fill up these orbitals, starting from the lowest to highest energy level, that determines the element's chemical properties.
Okay.
And that then dictates how it interacts with other elements to form compounds.
Hold on. So the entire periodic table, like the blueprint for all the elements, it's basically a consequence of electrons filling up these like weirdly shaped orbitals.
Yeah.
That's wild.
It is pretty wild.
And it gets even wilder, I bet, when we start talking about how those atoms actually bond together, right?
Yeah.
Because that's got to be those electron clouds interacting somehow, right?
You got it.
Okay. I am definitely ready to hear more about that.
All right.
But first, I think I need a drink, just to let all of this sink in a little bit. It's kind of amazing to think that these invisible clouds are basically shaping like the very fabric of our world.
Yeah. It really is incredible, isn't it?
Yeah.
Yeah.
All right. So I've managed to kind of wrap my head around all this talk about atomic orbitals and electron configurations, I think. And we've definitely established that, these electron clouds, they're not just some random fluff around the atom. They've got these specific shapes, these energy levels.
Right.
And that really dictates how the elements behaves, right?
Exactly.
But I'm still kind of stuck on how these clouds actually like help atoms bond together.
Yeah. So you're thinking about how you go from those individual atoms, each with their own like electron party happening, to them connecting to form the molecules that, make up everything around us.
Right. Exactly. Like how do you go from those little electron parties to like a giant bash?
Yeah. Good analogy.
Thanks.
So for now, let's focus on covalent bonds. And these are the ones where atoms are sharing electrons, right?
Right.
So picture this. You've got two atoms, they're approaching each other, each one with its own set of electron clouds. And as they get closer and closer, those electron clouds, they start to overlap.
So it's like two dance floors just like merging into one giant electron rave.
That's a great way to put it.
Is that what's happening?
Yeah, and within that overlapping region, those shared electrons, well, they're attracted to the positively charged nuclei of both atoms.
Oh, okay.
And it's that mutual attraction that's what holds the atoms together, forming that covalent bond.
So it's like those shared electrons, they become the glue, basically.
Yeah, you can think of it that way.
Holding those atoms together. Okay, but if the electrons are negatively charged, shouldn't they be repelling each other?
Right.
Like, wouldn't that make the bond, I don't know, unstable or something?
And that's where those orbital shapes, they come back into play.
Okay, they're important.
Yeah, remember we were talking about those dumbbell-shaped p orbitals? So when two p orbitals from different atoms, when they overlap, what they form is a region of really high electron density, but it's between the two nuclei.
Oh.
So instead of repelling each other, the electrons are concentrated in this like sweet spot where they're actually attracted to both nuclei at the same time.
So it's like they found the perfect spot.
Exactly.
Where everyone's happy.
Yeah, they're, keeping their distance from each other, but still getting pulled in by those positive charges.
That creates a strong bond.
It does.
Okay.
And keep in mind, the shape of those orbitals, that's what dictates the angles at which those atoms are going to bond. And ultimately, that determines the overall shape of that molecule.
Okay, so something as like abstract as the shape of an electron cloud, it can actually dictate something as tangible as the shape of a molecule.
Yeah, it's pretty amazing, isn't it?
That's pretty wild.
It is.
So are there other types of bonds besides these covalent bonds?
Yes, there are.
Yeah.
Another common one is an ionic bond.
Yeah.
And this is where basically one atom is going to donate an electron to another atom.
Oh.
And that creates two ions, and these ions have opposite charges.
Wait, so one atom becomes more positive and the other one becomes more negative?
Yes.
It's like a tiny little electron transaction?
Exactly, you got it.
Okay.
And those opposite charges, well, they attract each other, and that's what forms that ionic bond.
It's like they always say, opposites attract.
There you go.
Right.
Mm-hmm.
So covalent bonds, that's sharing electrons.
Yes.
Ionic bonds, that's transferring electrons.
That's right.
Okay, but you mentioned earlier that things get like even more complicated when we start talking about multi-electron atoms, right?
Right. So in reality, those electron clouds, they're not just like static little blobs. They're constantly interacting and influencing each other. And this leads to something that we call electron correlation.
So it's not just a peaceful little coexistence in that cloud.
Not exactly.
There's like drama happening.
You could say that, yeah.
Okay.
Remember, electrons are negatively charged.
Right.
So naturally, they want to repel each other.
Mm-hmm.
So that means that their movements are correlated.
Yeah.
They're constantly adjusting their position to, stay as far apart as possible, but at the same time, they're still attracted to that nucleus.
Oh, so it's like a delicate little dance.
Yeah.
You're trying to find that perfect balance between like attraction and repulsion.
Exactly.
Perfect.
And it's this dynamic interplay of forces that influences the overall distribution of electrons within that atom.
So these electron clouds, they're way more dynamic than like those simple diagrams that we see in textbooks.
Oh, yeah, much more.
But how do scientists even study something as, I don't know, intangible as an electron cloud?
Right.
You can't just like take a picture of it, can you?
That's where we have to bring in some really powerful tools and techniques.
Okay.
And one of those is something called density functional theory, or DFT.
DFT.
Yeah.
Sounds kind of intimidating.
It can be complex, but think of it as a way to simplify this really, really complicated problem.
Okay.
So instead of trying to track the movements of every single electron, which would be impossible,
Yeah.
DFT focuses on the overall electron density.
So instead of like choreographing the whole dance, we're just looking at the overall flow of the crowd.
Exactly.
Okay, I can dig that.
Yeah, it's like creating a heat map of the electron cloud,
Mm-hmm.
showing where those electrons are most likely to be found.
Gotcha.
And this allows scientists to study the electronic structure of even really large and complex systems, from molecules to, all sorts of materials.
That's incredibly useful.
It is.
So are there other ways to like see these electron clouds besides these like complex calculations like DFT?
Yes, there are.
Right.
There are a variety of experimental techniques that rely on the interaction of light and matter to kind of probe the secrets of those electron clouds.
Okay, and these techniques are called spectroscopy.
Yes.
And they're used in like tons of different fields.
Oh, yeah, all sorts of fields, from astronomy to medicine.
Wow. So by shining light on a material and then observing how it interacts, we can learn something about those electron clouds within its atoms and molecules.
Precisely. And different types of spectroscopy use different wavelengths of light.
Okay.
So, for example, X-ray photoelectron spectroscopy, or XPS. Yeah, that one uses high-energy X-rays to actually knock electrons out of the material.
We're like blasting the material with X-rays to see how its electrons respond.
Yeah, pretty much.
Okay.
And then by analyzing the energy of those ejected electrons, well, we can get information about the binding energies of those electrons within the material.
So that tells us something about the structure of those electron clouds.
Okay.
And there are other techniques like ultraviolet photoelectron spectroscopy, or UPS.
UPS.
Mm-hmm. And that one uses lower energy UV light to probe those outermost electrons.
Okay.
Which are, really crucial for chemical bonding and reactivity.
So we've got these theoretical tools like DFT to map out electron clouds. And then we've got experimental techniques like spectroscopy to like see them indirectly. It's amazing how scientists have figured out all these ways to study something that you can't even like really see.
It is pretty remarkable, isn't it?
Yeah.
And it gets even more mind-blowing, I think, when we start talking about how we can actually engineer these electron clouds.
Wait, engineer? Like, we can actually create artificial atoms with like specific properties that we want.
You got it.
How is that even possible?
Well, and that's where we enter the realm of artificial atoms, quantum dots, and superconducting circuits.
Okay, you're going to have to like unpack all of that for me.
I will, because I have a feeling we are about to enter a whole new level of, like, weird and wonderful in this electron cloud adventure.
Definitely.
Okay, so you were saying something about engineering electron clouds before the break. My mind is officially blown. We've gone from these like simple electron shell diagrams to talking about shaping and manipulating these clouds like we're playing a cosmic game of Lego. How is that even possible?
It all comes down to using what we know about quantum mechanics to control how the electrons behave. Remember how we were talking about those quantized energy levels earlier? Well, by confining those electrons in really tiny spaces, we can basically create artificial atoms.
Okay, so we're confining electrons in these tiny spaces.
Yeah.
But what kind of like tiny spaces are we talking about here?
One way to do it is to use something called quantum dots, and these are they're tiny semiconductor nanocrystals. They're so small you could fit millions of them across the width of a human hair.
So these quantum dots are like tiny little prisons for electrons,
Pretty much, yeah.
forcing them into those specific energy levels.
Exactly, and because those energy levels are quantized, these quantum dots, they can absorb and emit light at very specific wavelengths, and that leads to some really cool applications.
Like what? Give me some examples.
Well, have you seen those really vibrant QLED TVs that are getting, more and more popular?
Oh yeah, they're really nice.
Yeah. So the Q in QLED, that stands for quantum dot.
No way.
Yeah. They use quantum dots to produce incredibly pure and precise colors, so you get a much more realistic viewing experience.
So all those like bright colors on my TV screen, that's actually because of electrons being like trapped in these tiny quantum dots.
Yep, that's what's going on.
That's amazing. Are they used in anything else?
Oh yeah, quantum dots are being used in solar cells to make them more efficient, in biomedical imaging to track cells and molecules, and even in quantum computing as potential qubits.
Quantum dots and quantum computers.
Yeah.
That makes sense. But you mentioned another way to create artificial atoms using something called superconducting circuits.
Right, yeah. So superconducting circuits, that's a completely different approach. These take advantage of materials that have zero electrical resistance. Zero, but only at really low temperatures. So by designing circuits with specific geometries and properties, we can actually create artificial atoms that behave like those found in nature.
Hold on. So instead of like physically confining electrons in a tiny space like a quantum dot, we're using the properties of superconductivity to like create those artificial energy levels.
Exactly. And one key element in these superconducting circuits is something called a Josephson junction.
Okay, Josephson junction. What is that?
Basically, it's like a sandwich. You've got two superconductors, and they're separated by a very thin insulating layer. And the crazy thing is, even though, those electrons, they should be blocked by that insulator, they can actually, they can tunnel through it.
Wait, electrons tunneling through walls? That sounds like straight out of a science fiction movie.
I know, right? It's one of the many strange and wonderful things about quantum mechanics. And this tunneling behavior, it leads to those quantized energy levels in that Josephson junction. And that makes it behave like an artificial atom.
Okay, so we've got these two completely different approaches, quantum dots and superconducting circuits, and they're both creating these artificial atoms by like manipulating these electron clouds, which is just, it's mind-blowing to me. It seems like there's a lot of potential here.
Yeah, there really is. And both of these approaches, they rely on the same fundamental principle, quantum confinement. By restricting the movement of those electrons, whether it's in a physical nanostructure or through the properties of superconductivity, we can create systems with those quantized energy levels that mimic the ones found in natural atoms.
So it's incredible to think that we can like engineer atoms with specific properties. But why are we doing this? What's the big deal about having these man-made atoms?
The applications are they're vast. We've talked about the quantum dots and displays and solar cells, but the artificial atoms, especially the ones that are based on those superconducting circuits, they're really at the forefront of quantum computing.
Oh, quantum computing. That's like the holy grail of computation, isn't it? The kind that could like revolutionize, I don't know, medicine, material science, artificial intelligence, all that stuff.
Yeah, absolutely. And it all goes back to those electron clouds.
Uh,
By controlling how those electrons behave in these artificial atoms, we can harness the power of quantum mechanics to create technologies that we used to only dream about, that used to be science fiction.
It's amazing to think that something as like abstract as an electron cloud, it could have such a huge impact on technology, and it could really change our world.
And we're really just getting started. This field of artificial atoms, it's evolving so rapidly. Who knows what incredible breakthroughs are just, right around the corner.
It's exciting to think about. But before we get too carried away,
Yeah.
can you kind of summarize the key takeaways from our electron cloud deep dive today for our listener?
Sure, yeah. So we started out by basically shattering that myth of electrons just orbiting the nucleus like planets.
Right.
Instead, we explored this idea of electron clouds, these fuzzy regions of probability that actually govern how those electrons behave.
And we learned that these clouds, they aren't just random, like you said. They've got those specific shapes dictated by quantum mechanics.
Hmm.
And those shapes influence everything from how atoms bond together
Yeah.
to the properties of materials.
Yeah. And then we took a trip into the quantum realm. Remember all that? We were talking about electron correlation and exchange interactions, where those electrons are constantly kind of, pushing and pulling on each other within those clouds.
And we saw how scientists are using these amazing tools, from density functional theory to spectroscopy to study and map those electron clouds, even though they're so elusive.
Yeah, and then maybe the most exciting part, we talked about those artificial atoms, how we're using quantum mechanics to engineer atoms with very specific properties. And, that's opening up this whole new world of possibilities.
Yeah, it's been an incredible journey from the basics of the atom to the cutting edge of quantum technology. We've really seen how electron clouds are shaping the world around us, and how understanding them is leading to these incredible advancements.
And I hope our deep dives today has inspired our listener to keep exploring the mysteries of that quantum world. There's so much more out there to discover.
Well, that's a great note to end on. Thanks for joining us on this deep dive into the fascinating world of electron clouds. Until next time, keep asking those questions, keep exploring, and keep your mind open to the wonders of the universe.